Today we are beginning with section 6 of the syllabus and text, which is also the last section. So we're at the last leg of the syllabus. It is titled Space Physics and it has two topics: Earth and the solar system, and stars and the universe. And the reason you see me with the PDF open over here is because the chapter is mostly reading. Now, if there are certain concepts to understand, there's no technicality as such, and just one equation, I believe, that we need to deal with. So, let's get reading. It's pretty straightforward stuff.
Yes. Okay.
Zooming back in, just slightly zoom out. Okay. All right. So the Earth is a planet of the Sun traveling in a nearly circular orbit around the Sun, and the Moon orbits the Earth as a satellite. Now, if you want to revisit what a satellite is, I believe it was
Mhm.
oops, somewhere in Unit 1. Oh, here we are. All right, so satellites.
Okay.
All right, so it's given here. We can refer to that. So it's, you know,
Yeah.
an object that's orbiting another object,
Yeah.
basically. So the motion of the Earth and Moon accounts for the occurrence of a number of natural events, which includes the changing of day and night, and the changing seasons, and the tides as well. The motion of the Earth, day and night. The first thing you need to know is that the Earth has two types of motions. Right, one is obviously what we're familiar with is its movement around the sun, but the Earth is also moving on its own axis. So it's sort of spinning like a ball or a spinning top around what's called its axis. Right. So in this illustration, you see that line going from the north to the south. Right. And obviously, this is not there isn't an actual line, but right, that is considered its axis going through the center of the Earth, right, from north to south, and so it's revolving around, like it's spinning around the axis, and
Yeah.
it's also all while it's doing that, it's also moving around the sun, right? So there's two types of motions happening simultaneously. So the movement of the Earth on its axis changes which part of the world is facing the sun, and that's what gives us day and night. So when the Earth is moving, like on its axis, it's revolving on its axis, then the part facing the sun, forget everything else you're seeing here, right? So just what I'm explaining. The part facing the sun is obviously daytime, and
Yeah.
as the sun comes into view, that is the sunrise, and when it sets, right? I mean, when it's moving away from the sun, you get noon, and then sunset, and then right, when it's away from the sun, you get night, right? And
Yeah.
when it's night for us, the other side of the world experiences daytime, and that's what gives us the different time zones as well, right?
Yeah.
So there's a difference of 1 hour between where I am and where you are, right? And so that is because for me the sun sets a bit quicker as compared to for you, right?
Yeah.
Right. As for the so that's given here, the rising and the setting of the sun. So the sun rises from the east and sets in the west. Now, it doesn't happen exactly in the east, from the east and the west, the setting in the west, and the days aren't exactly like 12 hours because we have 24-hour day. So the days aren't exactly 12 hours each, except for twice in a year, which are called the equinox,
Oh,
right? And those are the 20th of March, approximately 20th or 21st of March, and the 23rd of September. So those are the times where the position of the Earth is such that day and night is split evenly.
okay.
Okay,
Yeah.
and so, right, all the other days, as we know, during winter, nights are longer and days are shorter, and as we move into summer, right, the days get longer, the nights get shorter, right? So it is only, between winter and March and between summer and autumn. I mean, right, obviously whether we actually experience those seasons depends on where we are, but so to speak, right, on these dates specifically is when you get, you know 12 hours of day and 12 hours of night.
Okay.
Also, the earth is tilted, right? So we draw it as if it's straight. No, it's tilted, so to speak, uh, right, with, the land area that we make. So if I can, have you seen a globe,
Yeah.
right? So if you've seen how they, like a good globe, the model of the earth isn't straight, it's
Yeah.
slightly
Right.
tilted,
Yeah.
and that represents uh, how
The,
the earth actually is, right?
the
So
position of the Earth slightly tilted.
yes, it's tilted by 23.5 degrees on its own axis. So if you see this,
Yeah. Yeah.
right, the very first picture,
Yeah.
right, the very first picture, and so you can see that's how the earth actually is, the second, the third, right? So proper globes are tilted. You don't have the straight ones, right? So the earth isn't like the straight images that we see over here. Okay.
Yeah. Okay. So right now, as we speak, there could be, another day started for other countries, right?
uh I mean,
Or
uh
night.
well, it could be like, there are times that we share. So it's evening, it's getting closer to sunset, and so for the other part of the world it's getting closer to sunrise. And so regions where there's like a 12-hour difference or so. And so what happens basically, for you, if it's like uh, 10 at night, and for them it's the same day but in the morning, like 8
Yeah.
8,
Yeah.
8 a.m or 10 a.m or whatever, right, whatever the time difference is. And so you do share the same day for like a for a small period of time, short period of time. But then obviously very quickly for us the date changes, and so they're still according to us in yesterday, and
Yeah.
we're in the future, as so to speak,
Okay.
right? Then is the position of the sun as we see it, right? So uh, during the winter, the height of the sun in the sky is at its lowest, and it's actually like not like it's lower during the winter, but there's a specific day when it's at its lowest, and that is the 21st of December.
And what causes that exactly?
Again, the rotation of the earth
Oh,
and around the sun and its own axis, right? So there comes a time where, right, I mean the sun's not moving,
the Earth is.
the earth is moving, right? And so basically, right, the way we are, the position of the sun as from what we are able to see from the earth, that changes.
So if there is a time where the sun is at its lowest, I'm sure there's a time where sun is at its highest as well.
Yes, and that is during the summer, 21st of June,
Okay.
right? And as you can see from the illustration on this
Yeah.
page, right? So this is the equinox, and so this would be like the standard position of the sun in the sky, so to speak,
Yeah.
right? This is in during the winter when it's lower, and this is during the summer when it's higher up, right? Noon is the time period when the sun is at its maximum height in the sky. It is fully risen it's at its maximum, and then it starts to set. So, right?
Yeah.
Uh, Also, right, as I mentioned, the equinox for the time, it's also right that it rises exactly from the east and sets exactly in the west, only on the equinox. So that's twice a year. Otherwise, in the northern hemisphere, so that's where we are, right? In summer, it rises north of east, so it's not exactly east, but north of east, and sets north of west. In the winter, it rises and sets south of east and south of west. But again, we're talking about the northern hemisphere, so that's where we are.
Yeah. Okay.
Right, so the longest day and all that is given over here. Talked about the axis, right? And so the rotation of the Earth around the sun gives us the seasons. The rotation of the Earth on its own axis gives us night and day,
Okay.
right?
Yeah.
So they are detailing that over here, right? They've labeled it A, B, and C, D, E, F, G, H, and all that. And so they
Yeah.
mention over part B, C, D, which is B, C, and D, right, of the Earth's orbit. The northern hemisphere is tilted towards the sun so that the hours of daylight are greater than those of darkness, right?
Okay. So does that mean uh does that mean the weather is also different in different country? Like
Well,
if we have summer, does that mean there's winter somewhere else?
well, the most obvious example is Australia, right? So we are moving out of winter into spring, and they are actually moving from autumn into from summer into autumn,
Oh,
right? So when we hit summer, they'll be in winter.
going opposite.
Well, it's because of the position, obviously, but yes.
Yeah. Okay.
So it's going to be cold over there, as per their geography, right? Whereas it's going to be hot for us.
Okay.
Okay. The southern hemisphere is tilted away from the sun and has shorter days than nights, so it is autumn and winter there. Right? So what we just talked about. The northern hemisphere receives more solar radiation, and so the weather is warmer overall. Over parts FGH, so this, right? The situation is reversed. The southern hemisphere is tilted towards the sun, while the northern hemisphere is tilted away from it and experiences autumn and winter. Right? So when it's winter for us, it's summer in the southern hemisphere. At sea, which is over here, around the 21st of June, the northern hemisphere has its longest day, while the southern hemisphere has its shortest day. At G, over here, around the 21st of December, the opposite is true, right? And at points A and E, which are the equinoxes, in both hemispheres, you have the same lengths of day and night. They're equal, right? So what's special about the 21st of June and the 21st of December, right? Having the longest day in the northern hemisphere on 21st June, and the longest day for the southern hemisphere on the 21st of December. Okay.
Yes.
Then we come to the moon. So the moon is a satellite of the Earth and travels round it in approximately a circular orbit. And it makes one complete rotation around the Earth approximately once a month. Right? And that's what is the like you get like a new moon, the cycle of the moon, right? Every year, sorry, every month, right? So that's the moon rotating around the Earth. And it's about like the moon's distance from the Earth is about 400,000 kilometers. The moon is also rotating on its own axis. Just like the Earth, the moon is also rotating around its own axis. And so we always end up seeing the same side of the moon, right? Because the Earth is rotating around its axis and the moon is rotating around its axis. And so right, that sort of synchrony gives us a view of the same side of the moon. Always, we don't get to see what is called the dark side of the moon, the other side of the moon. We don't get to see that from the Earth. Also, right, the moon is only visible because it reflects light from the sun, and right, it does not have any light of its own.
So why is that why it's not on the solar system? Like we cannot see the moon. Like
We can see the moon, we can't see it, like generally we can't see it during the day because the sun is so bright, right?
yeah, but
And it's like we are facing the sun, that's why, right?
okay.
But
So
during night,
yeah,
the moon is still there, right?
yeah.
So
So where is there? Like what position is it on? Does it come out of nowhere?
I mean, like, so when you are facing the sun, right? Obviously, it's daylight for you. It's daytime for you, and so the other part of the world is night, and that's where the moon is,
Oh, okay.
right?
Yeah.
But obviously, it's out there in space, so it is receiving just like we are receiving the sun's light, right? Part of the Earth is always facing the sun, so that way, similarly, the moon is also always facing the sun, some part of it. So when it's night for us and it's dark because we're not facing the sun, but the moon is, and so it's reflecting light from the sun, and we can see that.
Okay.
Also, the moon does not have an atmosphere like us, so it doesn't have oxygen, it doesn't have the layers, the stratosphere and the troposphere and the ionosphere and all those things that we uh, came across earlier in the syllabus. It doesn't have an atmosphere at all, right? So it's just the surface of the moon in space, so there's no oxygen, obviously. uh, it's vacuum over there. It does have a gravitational field because it has a reasonable mass. That gravitational field strength is only 1/6 of what we have on Earth. And that is why when you see a video of the astronauts who walked on the moon, right, they are like the gravity is less, so they're able to like bounce higher, so they're moving in a springy fashion, as they call it in the book, but they're not flying off into space because they were in space and there was no gravitational force attracting them. Then even the slightest movement would launch them into space for for as far as they could possibly go, until being attracted by some other gravitational pull.
Yeah. Okay.
Right, then is the phases of the moon. So we have the illustration on the next page. The moon's appearance from the earth changes during its monthly journey. It has different phases, right? So we see the crescent and then the half and then the full and then everything else, right? So we've seen the moon. And so in figure 6.13, the outer circle shows that exactly half of it is always illuminated by the sun, right? So we have the earth over here, right?
Okay. Yeah.
And the sun is down here. So the sun rays are coming in from the bottom of the illustration.
Yeah.
The yellow is, right?
The sun.
No, it's the part that's receiving the sunlight.
Yeah. Okay.
Okay.
Yeah.
How it looks from the Earth in its various positions is shown inside the figure, right? In the new moon phase, the moon is between the sun and the Earth, and the side facing the Earth, being unlit, is not visible from the Earth. A thin new crescent appears along one edge as it travels in its orbit, gradually increasing in size until at the first quarter phase, when half of the moon's surface can be seen. Right? So it's receiving light from the sun. The side facing the Earth is dark because it's away from the sun,
Yeah.
and so you can't see it from the Earth. Then when it moves, right, you can see that, right, it's receiving light, and so over here it was like only the dark side was facing the Earth. Now you can see like a bit of the light side, a bit of it, right?
Yeah.
And so you get to see something called the crescent, which is what we call the new moon. As it moves along from the Earth, right, you can sort of see half the moon. So as the first quarter,
Okay.
right? Then as it moves along, you get to see more and more of it. And finally, you see the full moon because the side of the Earth facing the moon is the side of the moon that's receiving the sun's rays. And oh, by the way, it's nighttime for you. So, right, you get to see the full moon in all its brightness.
Is it also because that the Earth is blocking the sun's light, which causes the moon to be full?
No, no, the moon is receiving like the moon is receiving the sun's light. It's
Okay.
just that, right, you get to experience the full moon because now the side of the moon that is receiving light is facing the side of the Earth that is dark.
Oh, okay. So it's more visible at
Yes.
dark.
I mean, it's not just more visible, more of it is visible.
Oh, yeah. Okay.
So let's go back to the explanation here. A thin new crescent appears, right? Okay. Along one edge as it travels in its orbit, gradually increasing in size until the first quarter, when half of the moon's surface can be seen. At full moon, the moon is on the opposite side of the Earth from the sun and appears as a complete circle. After that, it wanes. Wanes means becomes less through the last quarter phase until only the old crescent can be seen. So that thin moon that we see at the end before the month is complete. And so figure 6.14 shows the surface of the moon partially illuminated as seen from the Earth. Right. So this is the cycle, and this is an actual image of the moon. Right.
Okay. Is that was that picture taken up close as in
It's
um
it's it's probably taken with like a telescope or something.
yeah, okay.
Okay. Then, right, they like this is unless they've included the age of the universe. Let me just skip ahead and check. Have they included the age of the universe? Oh, they have. For you, they have. So there are just two equations there,
Okay.
right? This part is as a going further thing in O level. Right, so there's just one equation over here, which is about orbital speed, and it's pretty simple if you take a look at it. So speed is distance over time. So for an object like the moon in orbit around the sun, and the orbit is kind of like a circle. It's not exactly a circle. It's called elliptical. So it's like ovalish, right? as you can see in this illustration over here, right? It's not exactly a circle, it's more like ovalish, like a flattened circle. So that's how the orbit actually is. It's not like just round, perfect circle. So, but they're considering it to be a circle, and so, right, speed is distance over time. Average speed
Okay.
is total distance over total time, so we're familiar with that. And so what they're doing is like, okay, fine. So what's the orbital speed? And so that is okay. What's the distance of the orbit? So that's because it's round. We take the circumference, and the formula for circumference is 2 pi r, right? And what time does it take to travel the orbit, right? So 2 pi is obviously constant. So r is the average radius of the orbit,
Okay.
right? And so the distance from the Earth, for example, 40,000 kilometers for the Moon and the Earth, and t is the orbital period or the time for so how long, for example, it takes for the Moon to make one round around the Earth, right? And that's like sometimes 28, sometimes 29 days. Sorry, 29 and 30 days, right? So you putting those values in, we can get the average orbital speed, and this doesn't apply to the Moon only, right? You can get the orbital speed for, right, any planet or any satellite orbiting another celestial body,
Okay.
right? So even though it looks different, it's actually, distance over time. Distance is the circumference, time is time, how long it takes to travel that circumference. And we're done with half the chapter,
Oh, okay.
like half the topic. That's one chapter. Now moving to the solar system. And again, there's just like more stuff to know. It's just stuff to know. So the solar system consists of one star, like obviously our solar system, right? Consists of one star, which is the sun, in like what we call the sun, and eight planets. Eight planets because we kind of like kicked Pluto out.
Why?
Apparently, it was too small to be a planet, right? I mean, I grew up learning nine planets, and later on, I found out, oh, it's eight now. Sure.
That's rude. How bad for Pluto?
I mean, I read a meme where it's like, Pluto used to be a planet and now it's not considered a planet. But it made no difference to Pluto. Pluto doesn't care what you think about it. Be like Pluto.
Oh yeah. Let's go.
Okay.
Slay.
Yeah.
Okay.
So the solar system consists of one star and eight planets moving around it in elliptical orbit. So as I showed you in the illustration, right, slightly flattened circle, more like ovalish or oblong. It also includes dwarf planets and asteroids which orbit the sun. So everything in our solar system is like orbiting the sun,
Yeah.
right?
Yeah.
Uh, so asteroids which orbit the sun, moons that orbit many of the planets, and smaller solar system bodies such as comets and natural satellites. So there's stuff. The four inner planets. Why are they calling the inner planets? If you see the illustration on the right, there's the
Yeah.
sun. Then you've got four planets: Mercury, Venus, Earth, and Mars, and then just like an asteroid belt that is orbiting the sun,
Yeah.
right? And then you've got these four other planets: Jupiter, Saturn, Uranus, and Neptune,
Okay.
right? So within the asteroid belt are the what they're calling the inner planets, right? They are small, and compared to each other, they're like similar in size, maybe like slightly different in size, as like Mercury and Mars are smaller than Earth. Venus and Earth are about the same size. They are solid and rocky with a layered structure and have high density.
Okay.
The outer planets, so that's Jupiter, Saturn, Uranus, and Neptune, they are much larger. They are colder. One reason they're colder is because they're further away from the sun, right? and consist mainly of gases, and because of that, their density is low. The outer planets have many moons and other natural satellites in the form of icy rings of icy material. So you've got the rings of Saturn are famous, but the rings around Uranus and Neptune as well. And so those are like rock and ice that are in orbit around those planets, right? And I believe, is it like Jupiter or Saturn that has like any considerable number? Let's How many moons does Saturn have? And Saturn has, as of March 2025, right, which is just about a year ago,
Yeah.
Saturn has 274 confirmed moons. 274 moons for
Okay.
Saturn, right? Jupiter, as of early 2026, Jupiter has 95 officially confirmed moons.
Oh.
Then you've got Uranus.
Uh, Question.
Yeah.
What does the ring around Saturn and Uranus basically do?
What does it do?
Like, what's the why do they have a ring?
I mean, it's debris, it's rock and ice that is, you know,
Is it
within.
like a gravitational thing? Like, is
It
it?
is because like the whole thing with the orbit is like why are we in orbit around the sun, and why is the moon in orbit around us, like us as in the Earth, right? And it's because it is under the influence, and we are under the influence of the gravitational field of the sun, and the moon is under the influence of the gravitational field of the Earth, right?
Yeah.
And so we are that's why I showed you the satellite thing in unit 1, right, which was talked about under the topic of circular motion.
Yeah.
So we are, yeah. So yeah, in motion, circular motion, forces, and yeah, so circular motion, centripetal force, and then the satellites, right? So it is the centripetal force, which is the gravitational force in our case, that keeps, like at a certain distance, it keeps the object moving around, right? So the moon for the earth for the sun, the other satellites that, monitoring and communication satellites that they mentioned over here, that are in orbit around the sun, sorry, the earth, right?
Okay.
So yeah.
Um. So, is there like a possible chance that humans can go to another planet and adopt that environment and live there?
I mean, that is beyond the syllabus, but other than that, uh, from the little that I know, it is very difficult because our bodies are tuned to, uh, you know, the environment and the atmosphere and the conditions and the gravity and everything else on Earth,
Okay.
right? And so spending like just the time it would take to reach Mars in zero gravity or artificial gravity, and the conditions over there. I mean, you can't live on Mars because it's always like Mars, 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 right?
Yeah.
So you won't be able to live on the surface at least. And if you make life underground, you'll need to have an oxygen environment which is not there naturally, and other stuff. So
Plus
uh,
oxygen mask and everything.
yeah, so you need to constantly produce oxygen.
Yeah.
Excuse me. So
Yeah.
uh, Yeah, so I mean, on the face of it, it seems rather unlikely, but you know, if it does end up happening in the future, you'll see.
Yeah. Okay.
All right, now moving on, most of the dwarf planets, the best known of which is Pluto, so now they've categorized it as a dwarf planet.
Is it because it's the smallest?
It's because it doesn't qualify as an actual planet, but it is like larger than a moon.
Yeah.
It's
Okay.
not a moon. It's not a full blown planet. So it's somewhere in between, and so they categorize it as like a dwarf planet. And it's not just one. So it's, as you can see, they've written most of the dwarf planets. So there are others out there, right?
Okay.
Orbit the sun at an average distance greater than Neptune, right? So you can see it's way out there, and so it's also
Yeah.
orbiting the sun, but it's taking like super long,
Yeah.
right? Because even further than Neptune. There are trans-Neptunian objects. So there's stuff in between over here. And together with their satellites, number over 2000. They are generally of low density and are thought to be composed of a mixture of rock and ice. And so Pluto is known as like the frozen planet, right? It's like a ball of ice. Basically, it's rock and ice.
Oh. Okay. Okay. It also takes time. Is it because the gravitational does not reach the furthest to
Well,
Pluto?
it is under the effect of the sun's gravity. That's why it's
Or
orbiting the
it
sun.
is the weakest, right? Over there.
Comparative to Earth, the gravity is weaker, yes, right, compared to Earth. But
But it's still there. It's lingering
yeah,
around.
that's the reason why it is an orbit. If it weren't under the influence of the sun's gravitational field, then it would not be in orbit around the sun. But it is further away from the sun, and so obviously, when something's further away, right? I mean, the radius, right? So the inner circle, right, is is smaller radius, smaller circle. You move further away, the radius increases, the size of the circle increases. So that's basically what it is,
Okay.
right? Asteroids are pieces of rock of various sizes which mostly orbit the sun between Mars and Jupiter, right? So asteroids are mostly present between these two guys. As you can see, the asteroids over here.
So are they hitting Mars? Like which direction they go towards?
So right, their density is is similar, like density, right? Not gravity. Density is similar to that of the inner planets. As far as Earth's concerned, like your question about Mars, right? If they get close to Earth, because Earth has an atmosphere, when they enter the atmosphere, they experience like massive friction and then heat and everything, and so they basically burn up.
If there is no chance of entering it.
I mean, if it were like really big, like there was a scare some time ago that a massive asteroid is going to collide with the Earth, which it didn't. So, and they talk about an asteroid or a meteor. A meteor is like a piece of rock basically that's entered the Earth, and so that's what's assumed to have caused the extinction of the dinosaurs way back when,
Yeah.
right?
Yeah.
So if they enter the Earth's atmosphere, they burn up and fall to Earth as meteors or shooting stars. So if you've ever seen a shooting star, that's basically an asteroid that's entered the Earth's atmosphere and it's like passing by.
Oh. Okay. Okay.
Right, the largest asteroid, Ceres, is classed as a dwarf planet. So it's so big that's actually called a dwarf planet.
Like it's like as big as Pluto.
In that range, probably.
Oh shit. Okay. And the smallest one is called a meteor.
No, a meteor is like the asteroid, that's what's left of it after it's burnt up in the atmosphere. So if some of it, like in most of the times, it burns up completely, or like it's like so small, it's like pebbles or something, right?
Oh.
And
Okay.
so you don't really notice them.
Okay. Yeah.
But if it's sizable, then it falls as a meteor, and then you may have heard or read about or learnt about some areas of the Earth where there are craters. So the Earth's surface like sort of collapsed because of impact of the meteor. So let
Yeah.
me write is Ceres as big as Pluto? So Pluto is much larger, right?
Oh.
The diameter of Pluto is approximately 2,368 kilometers, while Ceres has a diameter of 950 kilometers approximately. So Pluto is roughly 14 times larger, like 14 times more massive than Ceres,
Oh. Okay.
but it's still classified as a dwarf planet.
Yeah. Okay.
Okay. So asteroids are presently classified as minor planets, right? Not dwarf planets, but minor planets, which are defined as, so what are minor planets? They are any object that
That is
orbits a star
okay.
that does not have a large enough mass for gravitational attraction to have pulled it into a spherical shape. Right? So they're not like circular like the planets that we know, right? And
Yeah.
so they don't have a large enough gravitational attraction because of their mass to be round, basically, as in circular. Larger asteroids such as Ceres are classified as dwarf planets. So what's the definition of dwarf planet? If they have enough mass and gravitational field strength high enough to have formed a spherical shape, but not enough to attract and clear the area around them of smaller objects. Right? So the area around Earth is clear. I mean, we've got stuff around the Earth, a lot of stuff, but we put it there ourselves. Right? The only thing visible around the Earth is the moon. Everything else was either like attracted towards the Earth, and that's it. So these dwarf planets have a high enough gravitational field strength to be round in shape, spherical in shape, but not high enough that it's able to attract the stuff in its gravitational field and clear the area.
Yeah. Okay.
Then you've got comets. Comets consist of dust embedded in ice, made from water and methane and methane, right? So we're familiar with methane,
Yeah.
right? So water and methane that freezes and makes ice, and then you've got dust inside of
Is it um as dangerous as the asteroids?
it. I mean, why would it be dangerous at all?
Uh,
Like
I mean,
if it enters the Earth's atmosphere.
yeah.
So comets themselves don't enter the Earth's atmospheres. Remnants, so what's left of them, right? Because again, just like asteroids, they will burn up, and it's made of ice, so ice will burn up. And so sometimes when we see that, right, whatever's left falls as debris, and it can be seen as a phenomenon called a meteor shower,
Oh, okay.
right? So
Yeah.
whole comets don't hit the Earth.
Okay.
Okay, so these guys are sometimes known as dirty snowballs. Their density is similar to the outer planets, so they have low density, and they orbit the sun in highly elliptical. So right, comparing the orbits over here, right, ours is not exactly a circle as you already shown, but just as a comparison, right, these are the orbits of planets, and this is the orbit of a comet.
Oh, okay. Okay.
Okay.
Yeah.
uh, right, in highly elliptical orbits and are much closer to it at some times than others. So at some point they're very close to the sun, like not like they're closer to the sun, at other points they are way off. They return to the inner solar system at regular intervals, but in many cases these intervals are so long that they cannot be predicted. Right, sometimes they go further away than even Pluto. On
Okay.
approaching the sun, the dust and gas are blown backwards by radiation pressure. So like we talked about there being dust, right? And so the dust and the methane is blown back because of the radiation of the sun, and that gives us the tail of the comet. I don't know if you ever seen it or you've seen it in some media like movies or animation or something.
Yeah.
And so the comet has a tail, and so that tail is the dust and the methane being blown back.
Oh, okay.
So the comet develops a bright head and a long tail pointing away from the sun. One of the most famous of comets is the Halley's Comet, which last visited the solar system, the inner solar system, sorry, in 1986, and it comes about every 76 years.
Oh,
Right? So, if that is true, if I'm still around, I'd be 75 when that happens. You'd be younger, obviously.
yeah.
I don't know, 75 or 74 or something, if I'm still around. Okay.
Yeah.
The sun is a star. Did you know that?
The sun is a word.
Is a star.
I mean, um, I have heard a few times the sun is considered a star.
It's not considered. It is a star, right? The stars that we see in the night sky are like similar to the sun in like they are suns as well. We call them stars like the layman term for star is what you see at night, but they're all there. The reason we can't see them during the day is because of the light of the sun is so bright that it
It hides.
yeah, so the light of the stars are much dim, as obviously because it's coming from much further away, right? And
Yeah,
so we can't see them. It's not that they disappear.
they're
And
there.
yeah, and so the sun is actually a star that is closest to us, and so that's why, right, we get light and we benefit from it. And it's the sun that we have is actually much smaller as compared to some of the other stars, or many
You
of
mean
the
there is bigger star than sun?
oh massive, like as small as we are compared to the sun is like that compared to some of the other stars out there. Absolutely massive,
Wow.
right? It's like comparing a ping pong ball to a football or a basketball.
Oh, damn.
Yeah,
Hmm. That's something.
right. So the sun is a star and produces its own light. The planets and our moon are seen from Earth by reflected solar light. Right. So I believe there's like an astronomical event that's going to happen on the 28th of Feb, I believe, when all the planets will be visible from the Earth.
You
And
mean you can see it without the telescope?
I don't know about whether you need a telescope. I haven't gone into the details, but they will be visible from the Earth and they will line up across the sky. Like you'll be able to see them in like a line. So
Oh,
I don't know whether you need a telescope or not. Like you can often see Mars and Venus. You don't need a telescope for those two,
yeah.
right? But the others will line up across the sky, and so the reason we're able to see them, just like we're able to see the moon, is because the reflecting light from the sun.
Yeah. Okay.
Right, elliptical orbits. So the planets, dwarf planets, and comets orbit the sun in an ellipse. The sun is at one focus of the ellipse, not the center, right? So one focus, one corner, one end of the ellipse. right? And again, right, they've drawn it very circular, but if we just go back, right, we can see that the movement of the Earth and the other planets is also similar. In this case, right, we kind of see it at the center, but right, there are points where the Earth is closer to the sun and points where it is further away.
Yeah. Can we take a break?
Just a few more.
Okay. Okay.
So for a comet with a highly elliptical path, the focus is not close to the center of the ellipse. For the approximately circular paths of planets, the focus can be taken as the center.
Okay.
Right. So next up, we're talking about the origin of the solar system and time, like how long it takes to travel, some info about the planets. I mean, honestly, this is stuff you can read on your own if you want to.
Yeah.
Right? This is just like reading.
A book.
Yeah, like it's just stuff.
Scientific book.
I mean, that is what it is, obviously. Right? I mean, they're mentioning the temperature and stuff. So, right, what I'll do is, if you want to take a break, after the break, I will like. How much time has it been? Okay, so it has been sufficient time. So, I'll talk about the origin of the solar system, right? Travel times and gravitational field strength, and then I'll leave this part for you, and then we can move on to the next topic.
Okay.
Okay.
Yeah.
So I'll see you in five.
Yeah.
All right.
Okay.
All right.
Bye bye.